I'm Michiel. I'm a student with Sandy, a PhD student, and I'll talk about algorithmic fairness. So as we know, machine learning sort of has gotten out of this domain of optimizing ad revenue or looking at email spam, but it has gotten into new domains, right? So it's used for hiring, loan approval, making crucial, oh, is my mic working? Yeah. Making crucial medical decisions, and even to inform bill. And these new applications, as well as the efficiency gains, have led to major concern for fairness, right? So do these algorithms introduce and perpetuate discrimination? And this is not without reason. So one of the more well-known and studied examples is an algorithm that was used by US courts to predict recidivism. So I think we saw this exact same picture earlier today, and it was about how likely is a defendant to reoffend, right? So how likely is he or she to commit another crime? And what turned out in a study in 2016 by ProPublica, that for black defendants that didn't end up reoffending, the risk score, twice as many had a high risk score as for white defendants. So even though this specific example, there has been a lot of debate over it, this did lead to a lot of additional research in fair machine learning. But what is exactly unfair about these algorithms, right? Should we just simply make algorithms that don't look at attributes like race? Is that leading to fairness? Unfortunately, this naive strategy doesn't work, right? So often things like race are encoded in other features like zip code. So the real story is more subtle than that. So let's take a look at this algorithm, which predicts recidivism scores, so how likely someone is to reoffend. And it does this for a red and a blue group. So below each person, you see a score of how likely this person is to reoffend. And if we now impose a decision threshold, so we say everyone higher than 0.5 is detained, everyone under 0.5 is released. Well, this seems fair to begin with, right? Because we have the same standard for every individual in our data set or in our example or in our algorithm of both groups. However, if we look many years later and we look at the people who actually offended, the probabilities can still be well calibrated, and even though the false positive rates or the error rates differ, right? So here we can, for example, calculate the false positive rate by looking at the people that didn't reoffend and were detained, divided by the total amount of people that didn't reoffend. And we see that we were actually discriminating against the blue group, right? So how can we solve this? So this problem actually turns out to be that you can't solve it efficiently. So the only thing you can do to have false positive rates equal and calibration still being correct is to do randomization. So you randomize part of the predictions for the advantage group. But this randomization sounds kind of weird if you look at important domains like criminal justice, right? Because this means that randomly you let people with a very high risk score out, right? So you release them, and people with a very low risk score, you detain them, right? So this is obviously not something we want. So we came up with a different method, and which is motivated by these adaptive systems. So many real-world problems are actually not so static as machine learning research make it seem, right? So often you can acquire more or less features at a cost. So look at this example for the medical case, right? So when a patient comes to a doctor or a hospital, it's not that the doctor collects all features and tests simultaneously to begin with. Instead, the doctor collects one feature, and based on the outcome, it collects more features, so more information, or makes a decision. It does this again and again. So you have a personalized set of information for each individual with personalized decisions. And you go on and on until you hit a certain confidence for every individual. I won't go into too much detail about our algorithm, but this is sort of what it's inspired by. And these adaptive systems you see everywhere, right? So in criminal justice, you can collect more or less information about a defendant, in credit assessment, in poverty prediction, and in many more domains and industries that we're seeing machine learning being used today. So at MIT, we created an algorithm that uses these risk scores and these properties of these adaptive systems to make an algorithm that actually can reach fairness constraints without resorting to randomization. And we showed the performance of this algorithm on a few public data sets. And we're even working now with an NGO to use this algorithm in action for poverty prediction in Latin America. So in summary, we've created an algorithm that's effective, that's efficient for budget-constrained decision-making, and that allows us to reach fairness. And as future work, we're looking at additional applications in credit, in insurance, in poverty prediction, and we're looking to extend also the theory and the methods to make our fairness algorithm more general. Thanks.